Hello, Ms. Schwartz's class, and anyone that is watching. This video is going to be on the Fundamental Theorem of Calculus Part 1. This is for Wednesday's lesson, and this is on page 13. The reason that I'm making this video for you is because, one, not only did I create this packet, but number two, Ms. Schwartz abandoned you, and I am here to help. You're welcome. You might wonder, and I'll keep this video in 15 minutes, under 15 minutes. You might wonder why Anna and Elsa are here from Frozen, for those of us that aren't aware of it. Number one, I have a 3-year-old daughter. And number two, my daughter is a huge fan of Frozen. We've watched it about 1 million times. That's not necessarily an exaggeration. And what you're going to find out today is the Fundamental Theorem of Calculus Part 1 is magical. Okay, so now that we got that fun stuff out of the way, here's fun. Get it? Fun because of the fundamental theorem. Fun. Okay, it looks like we have a differential equation here. F of prime of x equals x minus, whoa, hello. F prime of x equals x minus 3. So we have that differential equation there. We're limiting it between 0 and 7. And you'll notice now that we have something new here, and you won't see this again for another section when the Fundamental Theorem of Calculus Part 2 comes up, but we have a function equal to an integral. We have a definite integral this time also. We have integral from 0 to x of f prime of t dt. The first thing that you should know is that this is called an accumulation function. It's an area accumulating function. Area accumulating function. You'll notice also that when I write, my handwriting is not as good as Ms. Schwartz's, so too bad. Okay, this is an area accumulating function. And what that means is, given this graph, I can actually find some values on f of x based on this little equation that I have. And we're going to do that on the next slide. And I'm going to ask you to pause the video at points so you can actually try some of the problems on your own. I want to note that red disclaimer here. You are only ever going to have to do this process once. So this whole process that will take us about 7 to 8 minutes is only going to be done once, and then after that, you'll see the shortcut. And it's a really fun shortcut, and again, the shortcut is going to be the Fundamental Theorem of Calculus Part 1. It is truly, truly magical. So here is what you have on the page. I just put them side by side so you can see what's going on and for a little room for scratch work. Again, we have that differential equation. The differential equation is graph. This is a graph of x minus 3. We are bounded by 0 from x equals 0 to x equals 7 because that's what the constraints are. And again, this graph is the derivative. So it says that if I want to find f of 0, let's say, like if I want to find a new point, a point on the original graph, I could actually just plug x in. So for instance, if I wanted to find f of 0, notice not f prime, f on the original function, what I need to do is just plug in 0 for x. So I have the integral from 0 to 0 of f prime of t dt, and you'll notice that that doesn't go anywhere. From 0 to 0 was a quiz question. That doesn't go anywhere. So the point on f at x equals 0 will have a y value of 0. So we'll put a 0 here. Ms. Schwartz had actually, so when I made this packet, Ms. Schwartz said that she wanted me to put this little slot in, and it's a really good tip. That part is for an initial condition. And you'll notice in this problem that we do not have any initial condition. We do not have any initial f of something equals something. So because we don't have that, we can say that we have no initial condition. Okay, so a 0 plus the integral. And again, this is going to be a lengthy process. We're not going to do this every time. This is the only time we're going to do this. We are going to, my objective here is to build what the original function looks like using the area accumulator function. So we found f of 0. That's a point on the original graph. Let's go and find some more. We're going to fill in this table of 1, 2, 3, 4, 5, 6, and 7, and we are going to accumulate the area between f prime and the x-axis. So what I would do first, oops, somebody texted. What I would do first, and maybe you did this in the previous worksheets in the last unit, is I would actually just find each of these little values here. just so you have them, because you might need them. You do need them. So what I mean by that is find this area in each of these little segments. So what is that green area? What is that blue area? What is that red area? What is that red area? What is that purple area? Etc. Find each of these areas, pause the video, resume when you think you have them. But just remember, please pause the video. Please pause the video now. Thank you. Pause the video. So hopefully you found these areas. And again, these areas are for each one unit that you go over on the x-axis. If you weren't sure of how I got those numbers, you could count the boxes. So for instance, this red one, and I'll erase this in just a minute, there's 1 box, 2 box, and then a half box. So that's 2.5. It's negative because the value is negative because this area is underneath the x-axis between the curve, between the function and the x-axis. Okay, so now that we have that, we can actually keep going and find new values on f and construct that function. So let's go and do another one. And by the way, what shape do you think this is going to make once we have it? Keep that in the back of your mind. Let's go and do another value. Let's do f of 1. So f of 1 is going to be the integral from 0 to 1 of f prime of t dt. Okay, so we just said that when we find the definite integral, we're looking for the area between the function and the x-axis. So the function is f prime, and that means that in purple, I'm going to add these two areas up. I am accumulating the area. And it looks like I get a, oh, hold on, just for, sorry. Yeah, okay. I'm just for f of 1 means I stop at 1. I went on to 2 there. I stop at 1, which means I'm only looking at this area here. And that area is going to be negative 2.5, which means that, again, f of 1 is negative 2.5. I'll do another one with you because I kind of botched that one up. Let's go in and use a different color. So now to get f of 2, and feel free to write this in if you like. Oh, that's not the color that I want. For f of 2, I want the integral from 0 to, and again, notice where x is, so I can change that whenever I change the x value in f, 0 to 2. f of 2 is equal to the integral from 0 to 2 of f prime of t dt. And let's add up those areas from 0 to 2. So from x equals 0 to x equals 2 are those values. And if you look around where those numbers were, it looks like those were negative 2.5 and negative 1.5. So altogether, that's going to give me a value of negative 4. Okay, so that means that on f of 2, at x equals 2 on f, you have a y value of negative 4. For f of 3, again, we're just adding on more to that. So for f of 3, you're going to go ahead and add on this, this little triangle, which is going to be minus another 0.5, which gets us a negative 4.5. Please complete the rest of the table. Pause the video, complete the rest of the table on your own. Okay, assuming that you did the rest of the table on your own, here are the values that you should get for f. You should get those values. And if you got those values, you can plot them on the graph. So I plotted 0, 0 right here. I plotted 1, negative 2.5 right here. I plotted 2, negative 4 right here, etc. Okay, so I plotted those values. The reason I made them a parabola, and again, if you didn't plot the graph, you probably should, so maybe pause again and catch up. Pause the video, draw the graph, and catch up here. The reason that I got a parabola here is because I have a line. And if I think about this, because this is kind of what we did yesterday, I have f prime of x equals x minus 3. If I take the integral of both sides, okay, the integral of f prime of x was equal to f of x. The integral of x minus 3, the antiderivative is x squared over 2 minus 3x plus some constant. But it's not really any constant anymore because, again, I had a function, and I'll skip that explanation for right now. is x squared over 2 minus 3x plus c. The big picture here is that when you integrated the line, when you found the antiderivative of a line, you got a quadratic equation. And that is why we have a, that is why we have a quadratic equation. Oh boy. Hold on, just a minute. And that is why we have a quadratic equation down here. Okay, I hope that was clear, and if it's not, please watch the video or ask some of your friends in the class as to what's going on. You will not have to do this again for your homework, but the point is that you can actually make the original function point by point when given an area accumulating function. Okay, so now, here's what your graph looks like. That's just it plotted for you. I want you to find a couple values here, which you've already found. I want you to find f of 7, and I believe f of 7 is going to be 3.5, so let's go ahead and do that. This is on the next page if you haven't figured that out already, page 14. F of 0 looks like it's 0, so that's f of 0 is in green here, looks like 0. And it asks me for f of 7 minus f of 0. F of 7 minus f of 0, if I subtract these two, is equal to a whopping 3.5. Not entirely magical. Now look at the integral from 0 to 7 of f prime of t. Well, from 0 to 7 was all of this area and all of this area. Well, let's see here. If I go back to that picture, let's just see how much area I actually have. Let's go back one more slide. So the integral from 0 to 7, I had a total of negative 4.5 in red. And then in green, if I add that all up, I have 7. So I have negative 4.5 plus 7. So when I accumulate all of that area, let's see, when I accumulate all of that area, I have a negative 4.5 and a 7. Negative 4.5 plus 7 is equal to 3.5. Coincidence? I think not. This is the fundamental theorem of calculus part 1. And here's what it is. Here's the magical part. If you take the integral, get ready for this. If you take the integral from 0 to 7 of f prime of t dt, it is equal to f of 7 minus f of 0. This is called the net change of the antiderivative. The net change of the antiderivative. Okay, this is the fundamental theorem of calculus part 1. You can find the area between the curve and the x-axis. And when you do that, that is going to be the equivalent of finding the net change of the antiderivative. And I'll give you a hint, you actually aren't really finding the area directly on your homework assignment. Ms. Schwartz is going to walk you through in her video of how to actually apply this with a few example problems. But again, it's actually a really interesting idea that if you find the area between the curve and the x-axis for some constraint from 0 to 7, in this example, that is actually equal to f of 7 minus f of 0. And just because I have the extra minute, I'm going to use it. I think we said f of x was equal to x squared over 2 minus 3x plus c. Take a look at this. If it was x squared over 2, so f of x was equal to x squared over 2 minus 3x plus c. Better hurry, Mr. Lakin, you're almost out of time. If I plug in f of 7, then f of 7 is, let's see here, I get 49 over 2 minus 21 plus c. And then if I do f of 0, okay, f of 0 is, oh, I hope this works, is just c. And I subtract those two. Okay, so let's subtract those. Oh boy, I don't know if I can subtract those. If I subtract these two quantities together, then what I end up getting out is 49 over 2 minus 21. Okay, let's see what that is. 49 over 2 minus 42 over 2 for a common denominator is 7 over 2, which is, it is 3.5. Oh my gosh, that's amazing. to finish up the video, and that's what you're going to be doing, by the way. To finish up the video, let's see where I am now. Let's delete that page. Let's unpack this again. I'm over my 15 minutes just because I went on a tangent. Tangent. Funny. So, here's what you're filling in here. This is the fundamental theorem of calculus, part 1. There's part 2, which you'll see in next week. The integral from a to b of f prime is equal to f of b minus f of a. What that means is the definite integral is the net change of the antiderivative. Antiderivative. And as you can see here, my boxing tool has eluded me once more. I would box in that last sentence because that is the most important sentence you could possibly imagine in your entire existence. So let us just put a box in here. And you're welcome to stop the video if you got bored of me already. That's fine if you got bored. I'm not offended. I'm a little offended. Here's the box. Oh, look at the fancy box. And again, this is only true, by the way. I hope nobody paused the video and quit. This is only true if a function is integrable. Looks like differentiable, kind of is integrable, which means that the function must be continuous. This does not work if you have a discontinuous function somewhere on the interval. Okay, so now that we know what integral is, let me go ahead and show you my amazing acting skills as I go through this scene. Begin A-B planning session, discussion scene with Mr. Lakin and Ms. Schwartz. Mr. Lakin, hey Schwarzenator. Ms. Schwartz, what's up, Blanket? Mr. Lakin, do you think students know how powerful that the fundamental theorem of calculus part 1 is? Ms. Schwartz, as long as they know that the equation is not static. Finn, okay, let's take the equation and show how the equation is dynamic, and this is an important part. If you have the integral of a to b of f prime of x equals f of b minus f of a, what you can actually do to make this not static is actually add the f of a to both sides of the equation. And look at that, now it's alive. So form 1 is f of a plus the integral from a to b of f prime of x dx is equal to f of b. So we could use that little part, some initial condition plus the integral, to get a new y value on the function. That's pretty nifty-galifty. Similarly, we could solve for f of b if we wanted to, and say f of b is equal to the integral from hold on just a second, I did that wrong. We could say similarly that f of a, rather, let me write f of a is equal to f of b minus the integral from a to b of f prime of x dx. So pause the video and write down which form you like the most. Please pause one. I'm sorry, please choose one and pause and write, and then let's go to the next slide when you're done. Almost done, guys. Remember this little Bitmoji scene from packet number 1? It's on the front page if you didn't see it before. And it says that the end of something is equal to the start of something, like an initial condition, plus an integral where you have a start time and an end time and you are accumulating something. Again, it's a super important idea for AP, and you should probably talk with your group about how that equation relates to the story of your life, and you can recap those stories to Ms. Schwartz when she returns in January rather. And that's all for this video, guys. Thanks for watching.